Hello, everyone, and welcome back to our favorite show. I'm just gonna let you go ahead and just get it all out the way. He's gonna tell you exactly who he is because we're not doing no guessing today because we have a great movie coming out this weekend and we're here to promote it. It's called Oppenheimer. Y'all should check it out. But we're gonna get to this interview. So, first off, our special guest, please tell us your name and tell us something about your specific project that made you so significant. Hello, my name is Arthur Holly Compton. I am an American physicist from Wooster, Ohio, originally. So I kind of started my journey, I would say, at Washington University after I attended graduate school in Princeton. So after Princeton and before I went to Washington University, I was able to do a fellowship at Cambridge, and this kind of initially got me into the idea of working with X-rays and working with gamma rays. So specifically with X-rays is the project I primarily focused on. And so as I was doing research, I conducted several experiments and I just kind of noticed the little bit of discrepancy in the classical thought of how wavelengths would perform based on scattering these light. And so with that, that kind of project centered around what these different frequency phenomenons we were seeing were actually coming from. And so we kind of used that methodology and thought process to develop this kind of overall thinking pattern of what it should look like. And that kind of led to our project that ultimately dealt with how X-rays scatter light and what is now known as the Compton effect. Wow, that is fascinating. So, what exactly were you trying to find or do with this project? So, as I previously kind of touched on a little bit, so when we were kind of examining these different frequencies, the classical line of thinking is that these frequencies would have an incident frequency, and when they would scatter, they would come out and they would ultimately have the same frequency on the other side. So when I was kind of analyzing the data and seeing exactly what these X-ray particles were kind of doing with these frequencies, I noticed that there was a shift in the frequency. So for some reason, there was a shift and there was a small decrease in the amount of energy, and then it would cause the wavelength to lengthen. So with that, I kind of thought this was kind of weird that it was against the conventional mode of thinking. So I took that opportunity to explore further why exactly this phenomenon was occurring. Wow, so where exactly did these experiments occur and what were you doing in order to conduct this experiment? It sounds like very high level stuff. Conducted most of my experiments in my lab at Washington University. So I conducted most of those while I was also the head of the department there at the time. So it was a bit challenging to navigate working with that dynamic, trying to untangle this big problem I found and also being the head of the department. But I was kind of so involved in figuring out what exactly was going on with these frequencies and these wavelengths that I was just like, I need to dive in and get to the root of the problem. So the actual experiment was conducted in my lab, kind of using this whole system that was set up. So initially the system starts out with what's called a Crookes tube. So basically this is like a glass kind of light bulb or basically light apparatus. And what this does is it allows us to send these X-rays through a crystal. So we use a crystal in order to scatter the light, and the light goes through the crystal and then goes into what is called an ionization chamber. So in this ionization chamber, basically what you have is these X-rays will go and they will hit and they will ionize and basically cause electrons to basically scatter. And what these electrons will then do is they'll allow a current to be measured. So when we measure this current, we utilize what's called a 4-quadrant electrometer in order to measure how much current there currently is in the system. And then we have a film at the end of that, so that way we can have nice pretty data and see how this all fits together. So basically the more X-rays we have go through, the more current and charge we will see at the end of this in the 4-quadrant electrometer. So basically, what made all this happen is basically this Crookes tube would send out X-rays and it would bounce off a crystal, and different crystals would function differently. And what we did kind of see is that we could basically change the angle in which the scattered light would scatter, and this would ultimately change the wave function or wavelength that you will see coming out of that light. So that shift in difference is what we were kind of seeing. And what I would do is I would play with the angles, and this is kind of how the whole experiment started to begin. And what I found most intriguing was at first I never even noticed this. And so it was kind of one of those things where, you know, you go back over the data, and I kind of made a few mistakes in the beginning, but ultimately I caught it, and it really just took off once I was able to really hone in and see that in order to impact significantly what kind of different wavelength we were going to get and ultimately change the amount of energy was all dependent on what kind of angle we scattered that light out at. Interesting. So, was there anybody else involved in this project with you? That's a very good question. So, I primarily worked on all of the project and everything to do with this kind of idea primarily by myself. So, the whole premise of why I chose to go to Washington University in the first place was there was a lot of kind of thought process going on at the time, and everybody had their own ideas and inputs of what exactly was going on with x-rays and kind of the ultimate understanding. So I didn't want a lot of the outside noise to impact my kind of thinking and my thought process. So I just went to Washington University to kind of be isolated on my own, and that kind of is why I did a lot of this projects and all the kind of overall data collection and stuff by myself. And I primarily only used collaborators to help reinforce the ideas that I already had. So kind of a lot of the thinking was the collaborators would just strengthen the overall argument, and once I kind of developed everything and kind of saw, they kind of added more sturdy foundation to everything that we already had discovered. Interesting. So were there any significant events or anything going on around the world at this time? So during this time, kind of like when I was going to start initially grad school, was like the pinnacle of World War One. So the world was kind of basically in limbo at this time. But ultimately, if you go back to what really started everything, was basically Wilhelm Röntgen in 1895. He basically discovered X-rays. So I was about, just a few years born, but by 1901, he got the Nobel Prize for this discovery. So then, kind of, you fast forward like a decade or so, you see Max von Lue. He kind of showed that diffraction of X-rays was possible, and so kind of once these two things happened, where we saw X-rays were a thing and diffraction really took off, is when ultimately X-ray studies and X-ray research kind of became a staple and kind of what everybody was focusing on. So I kind of just piggybacked off that, and I kind of did a little bit of undergraduate research work with X-rays and a little bit of spectroscopy work, which was shown the previous year by another Nobel Peace Prize winner. And I also, when I went to Princeton, did a little bit of work with X-rays and electrons. So that was kind of basically the basis of my dissertation. So once I kind of dove into that and I had my fellowship and worked a little bit with like gamma rays in Cambridge, that was kind of when I saw those two things align, and that was kind of what was the big focal things going on at the time during the world. Interesting. So, what overall impact do you think that your project had on the physics community and world as a whole? As I kind of touched on, my project basically honed in on this idea and reshaping the classical opinion that basically if you have an incident wavelength and you scatter this light on the other side, you will have come out an equal or the same wavelength. So when I saw this shift in wavelength based on basically small atomic crystals or particles or atoms, when you scatter light off those, you will see a shift in frequency, or you'll see a decrease in energy and then a shift in this wavelength. Now, it doesn't always happen, and it's not all the time. And so the difference in this kind of scattering is elastic versus inelastic. And so elastic, what you will have is you will have that same kind of wavelength come out on the other side once you scatter it. But inelastic, you will see the shift. And so what my overall thinking and process was when I noticed that this kind of shift was occurring, I went through and worked out a kind of formula when what I found and deduced was that ultimately light is made up of waves and particles, and these particles I termed as photons. So these photons, they would come in and interact with an electron, and what this would do is once they interacted, it would cause that photon to lose a bit of energy in this transfer from this collision. And so what I used was the idea of conservation of momentum to deduce that in order to lose this energy, some of that energy had to be transferred to the electron. The photon would lose some of that energy, and what that would cause was an increase in length and wavelength, and which is why you saw a shift. And now this shift is very subtle to the eye, but it was actually very significant, like data and statistically. So this is kind of ultimately what I deduced in order to kind of figure this out. And basically what I found was based on the scattering angle that the light kind of scattered at, would it kind of indicate and hone in on what exactly that wavelength was going to be when it came out. So you could pretty much dial in exactly the kind of wavelength you wanted to, dictated based on that scattering angle. And so what this did was it kind of basically one, it kind of solidified the idea Einstein had of light being made of particles. So it was based on his quantum theory idea, which I hadn't known too much about, but I was told kind of a little bit longer down the line that this was something that he proposed, and everything kind of fit inside there. And then it also inspired other physicists down the line, one being Louis de Broglie, who kind of honed in on the idea of wavelength, and other physicists down the line to kind of expand and kind of use this notion and the idea of the Compton effect, which has been come to known as. It's always so hard for me to say that because it wasn't kind of what I was thinking of at the time, but it kind of inspired these people to go off and use these new theory of quantum mechanics and quantum theory to kind of develop new ideas, which I personally think is very interesting and cool. Wow. So, what led you to conduct the research on these x rays in the first place? What I touched on a little bit earlier was what primarily interests me in x rays and kind of diving more into the x ray research was just like the early kind of ideas and a little bit of spectrum work I had when I was in undergrad. And then it kind of allowed me also to do a little bit of work with my brother. So we kind of were able to really hone in on our spectrum and kind of hone in on the four quad spectrum I told you about. So we were able to get it very, 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 very fine tuned in order to really analyze very, very small changes in current and very small amounts and kind of how much is going through, and able to really enhance the data collection we're doing. On top of that, I became really interested in glass blowing when I was younger. So kind of what really allowed me to expand my research was when I talked about the initial ways that we would kind of shed the light using the Crookes tube. And so we would kind of take those x-rays and send them through a crystal. I was able to develop my own using my glass blowing methods that I had perfected, and kind of make the perfect system in order to really kind of get the most amount of x-rays through the crystal to really see how significant the changes were in these energies. And so I think that really kind of elevated my research. And since I could do it all myself, I didn't have to wait for them to be made, or the kind of imperfections that we're going to be doing and getting when I had to go out and get them myself. So that kind of really elevated, not only helped me take a little more personal kind of feelings about x-ray research, but it kind of helped elevate that. And then kind of was like really facilitated all by when I was able to get that fellowship and go to Cambridge. I wasn't exactly studying x-rays, but studying gamma rays, which is kind of like just a step over, a step to the side, just a different kind of research, kind of allowed me to really hone in when I came back from being abroad and kind of what I wanted to do and kind of the ideas I wanted to come to Washington with and develop further on. So on my trip back, I had a lot of notes I developed and things I wanted to accomplish when I got to Washington. And as soon as I got there, I was kind of able to hit the ground running. And so during the time, there was a lot of people doing not just specifically X-ray research. There was all across the spectrum, but I kind of wanted to hone in on the X-rays because it was been something I've been working so long with, and I've been able to develop kind of my own implementation to kind of make it my own and really utilize my skills that I developed over the years. So, was there any other work or anything you did after you were awarded the Nobel Prize? Did there anything else you discover, any other work you were doing? After the Compton effect work and the project I did that allowed me to earn a Nobel Prize, I primarily did a lot of work with cosmic rays. So I primarily looked at the intensity of these cosmic rays, and this kind of led to a longer, more widespread study specifically of the magnetic fields of Earth. On top of that, I wrote a book about X-rays and electrons. You all should check out. It's a fantastic book. And I was able to be a part of a team that was working on what is now known as the Manhattan Project. So with this, I did a kind of a lot of research and hands-on things that led to a lot of significant research. And I hear they might be making a movie about it. So maybe you should check it out. Could be a good watch. Wow, well, that was fantastic. I thank you all for listening to our project and our overall show today. If you have any questions, please leave them down in the description below. And please don't forget to like and subscribe to our channel and give us a fantastic review. Have a good one.